Okay, let's start. Yeah, it's a really great pleasure to come to Princeton and also like thank organizer to give me a chance to talk here. It's a really wonderful summer school. And I was a postdoc in IIS for maybe 30 years ago, and before that I was a student in Princeton. So coming to Princeton, like to me, like a kind of homecoming. And today I'm going to talk about generalized symmetry, but from some top-down point of view, some kind of summary. The generalized symmetry is a field launched by this paper, and so this top-down view is kind of like this bird-eye view. But the bird-eye view also have another interpretation, is that you look at the things from one higher dimension. So I'm usually using the both meaning of a bird-eye view here. So what is the symmetry? We know that the symmetry basically is given by a transformation, which is labeled by the group, and this transformation act on the Hilbert space, which have a tensor product decomposition. And using the transformation, we can define so-called local symmetric operator, which commute with the transformation, and which form an algebra. And the Hamiltonian is just sum of some local symmetric operator. And also, importantly, the allowed symmetric perturbation is also given by this local symmetric operator. So we see that the local symmetric operator play a key role in defining symmetry. So this led to another way to define symmetry. By abandoning the transformation, now we no longer use transformation. We just use a local operator. But the local operator we use is basically is a choice of a subset of a local operator. Every choice of such subset corresponds to a choice of symmetry. Basically, symmetry is a choice of a subset of a local operator. So we're taking that point of view. We no longer use a transformation to determine, to select this subset. Okay, certainly this subset should form an algebra in a sense. The operator in this subset is closed under addition, multiplication by complex number, and also this subset is closed under the operator product. And so this really, we call this a so-called the local operator subalgebra. And so the point of view is that the symmetry is actually given by a local operator subalgebra. So this is another way to look at the symmetry. Okay, and certainly if you choose all the local operators, not a subset of local operator, then that's correspond to a case with no symmetry. So the algebra for all local operator is correspond to no symmetry. But if you choose a subset of a operator, then you have some symmetry. So in some sense, this some symmetry is turned out to be generalized symmetry. So one can view generalized symmetry from this algebra, operator algebra point of view. Okay. So from this, then from this operator algebra point of view, it's naturally there is a equivalence. That is this isomorphic operator algebra should describe the same symmetry. Okay. And because if you choose if two different subset, but the operator algebra is isomorphic, then they describe same symmetry. So therefore we call this so-called same symmetry or equivalent symmetry called the hollow equivalence. The hollow really become holographic. For the meaning will become more clear later. Okay. And but certainly here probably need to go a little more than this algebra isomorphism. If the symmetry is this subalgebra tensor product with another algebra with no symmetry, that means algebra of all local operator, we should have same symmetry. So therefore this relation also define the equivalence. So I think so these two equivalence relation probably define this hollow equivalent class of symmetry. So this hollow equivalent class of a symmetry is called the categorical symmetry. So basically, by definition, it's an isomorphic class of a local operator subalgebra up to this tensor product with this algebra with no symmetry. So this is just a definition. Okay, so let's just give an example. What I described is very maybe too abstract. So let's consider a two-dimensional model. In one model, we have a spin 1/2 live on the side. In another model, we have a spin 1/2 live on the link. Okay. Then this is a subset of local operator algebra. This local operator subalgebra. Local operator subalgebra in the first model is generated by this neighboring z operator on the sides, and also the single x operator also on one side. Okay, so this basically generated this some kind of like icing model. Okay, and so this ZZ operator and x operator generate all other allowed operator subalgebra. In the second model, we have similar thing. That's for the operator on the link, we have a z operator on the link, actually which also corresponds to the ZZ operator in the first model. And then we have this kind of plaquet operator near the side on the full link attaching this side k. So it's a full x operator. Okay. And by design, actually, one can see that there's a correspondence between the operator in these two models. The ZZ in the first model corresponds to Z in the second model, and the single X operator corresponds to full X operator in the second model. And you can check actually the operator algebra, like a commutation relation of these two set operators is identical. I purposely labeled them the same way. So this the corresponding operator have identical operator algebra. Okay, so this is an example that these two different choice of a local operator size algebra gave rise to equivalent symmetry. Yeah. So these two models have equivalent symmetry. Okay, so now let's consider symmetry in a more traditional way. I mean, here I described this hollow equivalent class of a symmetry. So let's look into the class to see what's in this, inside this class. So here we'll introduce a symmetry transformation. Okay, to look into this equivalent class, we introduce a symmetry transformation. Before we did not even introduce a symmetry transformation. Here the symmetry transformation also form algebra. So the operator for the symmetry transformation operator which commute with all the operator in the local operator subalgebra is a commutant of a local operator subalgebra. And those transformation operator also form algebra. Okay, so therefore now we're using more traditional point of view, using symmetry transformation algebra to describe symmetry. And certainly we also have a similar thing like this isomorphic algebra of the symmetry transformation describe the same symmetry or equivalent symmetry. But this equivalence is smaller than the hollow equivalence I described before. So it's a smaller class. It's a more refined characterization. So here I want to say that actually the algebra of a symmetry transformation depend on the topology of a space. Usually we say the symmetry is symmetry, it doesn't matter how you choose your system or the space of your system living. But actually this symmetry algebra depend on the choice of a space. Simply, for example, if our spatial manifold is not connected, so have non-trivial pi 0, then on every piece of a manifold, we have an independent symmetry. So actually the symmetry algebra is a tensor product of the symmetry algebra act on each piece of a space. And certainly for higher symmetry, even pi 1 of a space would enter. So so this is just a kind of interesting property of this symmetry transformation. Actually, it's depend on spatial topology. Okay. And so then from this operator algebra point of view, we can define what is a invertible symmetry, what is a non-invertible symmetry. Okay. So basically is that if you can find a set of a generator of this operator algebra, and which kind of like a group generator, kind of like a group permutation, then we say, oh, this is like a invertible symmetry. If such a set of generator do not exist, whatever generator you'll find, they always form algebra rather than this group algebra, more general. They form a more general algebra. Then we may say it's a non-invertible symmetry, or we call it an algebraic symmetry. So yes.
When you discuss local operators, do you exclude line operators?
Yes. So local operator really local. Local means they act on the single site or neighboring sites. Then that's it.
But that means that you would not include in this definition hyperpoles.
It has. You'll see. Yeah, it is there. So yeah, so-called this local operator subalgebra is generated by local operator. But as an algebra, actually, you can multiply many operators together, you can get a pretty big extended operator. So actually, this local operator algebra is it's quite complicated in the higher dimension, and it does contain extended operator. I think you'll see that actually this extended operator really play a key role in determining actual symmetry. So here, just a definition, but we don't see group. We don't see any mathematical structure which really characterizes symmetry. It just formally define an equivalence class here. And but on the hand, I introduced this way because this is kind of microscopic. It's something on the lattice you can see. But eventually, the goal of this talk is that to extract from this local operator algebra the group structure or some category structure, which actually describe symmetry in a microscopic sense. So this is a very microscopic description. So now here is the answer to Natty's question. So what is the symmetry transformation algebra of for the two examples we just discussed? You know, and we want to find the operator which commute with all those local operators. Basically, because we have a single X operator on single site, then the operator commute with all the X operator must be only the product of X operator. Okay. But not so any product of X operator will be fine. Okay. But however, the condition on is commute with the ZZ operator on the neighboring sites really says that the power of X on site I and the power of X on site J should be equal. So therefore, they would commute with this operator. So that means it's a product of X operator, and it's actually present on every site like a constant power. So exponent of X is constant, is I independent exponent because of this condition. Okay. Then it's I think it's I don't have proof, but you probably can see by that for this first model, the transformation algebra generated by the product of X operator on every site. Yeah, but certainly if the space is not connected, then this the exponent of this X operator can depend on which spatial component you are in. The different spatial component may have different exponent, 0 or 1. So that's why on different when the space are disconnected, you may have several. This algebra is actually different. Then for the second model, again, because we have a Z operator on every link, then the operator commutes all the Z operator should be just a product of a Z operator, which live on the link. Okay. And then this, but this the product of Z operator connect with commute with the 4X operator. Basically say that this operator should define on the loop. For any loop on this square lattice, if it goes through this 4x operator twice, so they will commute with this 4x operator. So that's a one form symmetry, so therefore the symmetry for the second model actually is generated by this loop operator of X.
The one-form symmetry, one of the characteristic definition that you put.
Hmm?
The one-form symmetry.
Yeah.
Is defined in the second paper.
Yeah. Yeah, yeah.
Symmetry of your model is not.
It's not topological, yes.
So it's not a one-form.
Yes, yeah, there's a, yeah, indeed, there's a subtlety. There's a lattice story, there's a field theory story. Yeah, this one is not topological. Actually. So this is maybe a non-topological version for one-form symmetry. Yeah, in the lattice, yeah, indeed, there's a subtlety. Yeah.
Very specific for this model. There's a huge symmetry.
Yeah.
A lot of models the nuke with a zero-form symmetry.
Yes.
And that can tiny subset. In fact, it's not a subset, but the quotient is the one-form symmetry. That's very ugly.
Yeah, and in some sense, this symmetry operator act non-trivially, maybe only when they have a non-trivial loops. For the contract loop, their subspace they act trivially, you can quotient that out. And this, yeah, I just describe this the lattice version of the story, which, yeah, for every loop we have a different symmetry transformation. So indeed, the symmetry transformation for deformable loop are different in this lattice version. I think in the field theory version they are identical. There's a I try to say that the field theory version is it's kind of like a projection in some subspace of this lattice version. But anyway, maybe I should say this: the so-called one-form symmetry here is really is a non-topological one-form symmetry. I mean, maybe you can say that it's some kind of transformation. But there's a lot of transformation. Not like here, there's only one single transformation. And this is algebra generated by many transformations for a very large loop. Yes. Projector what? Okay, the point is that for this transformation algebra, it's defined so-called symmetric local operator. So those local operator commute with every loop operator here. So define this symmetrical operator. Then we play a game like a Hamiltonian must be some of a so-called local symmetric operator. Then we say that Hamiltonian have a symmetry. Then if you do symmetric perturbation, the perturbation must be selected from those symmetric local operator. So that's the game we play. Then that define the rule basically. Yeah. Okay. So so actually these two models is kind of interesting because so basically one is a zero form symmetry, another is this non-topological one form symmetry. But also say that these two symmetry are actually hollow equivalent. So this example, the two seemingly very different symmetry actually equivalent. They are equivalent in the sense the phase diagram of these two models with these two different symmetry actually is have one-to-one correspondence. And the corresponding phase transition and the critical point is the same. And the low energy spectrum for the local excitation also is the same. Only some topological sector may be different, but the local property are the kind of the same. So so that suggests that these two models have some duality relation. Indeed, there is a duality relation between the two through the gauging. I think yeah, probably I don't want to show when we talk about this stuff. And so the point here is that when we have a hollow equivalent symmetry, it suggests that there is a duality transformation mapped from one symmetry to another symmetry. Another interesting consequence is that if you do not have any symmetry, then there's no duality. I think the point of view from here is that if your model don't have any symmetry, there is no duality transformation. But if your model have a symmetry and the symmetry can be mapped into another hollow equivalent symmetry, then there's a duality map, which map this model to another model with a hollow equivalent symmetry. So the duality and the symmetry have very close relation. Okay, now we have here's just some more example for this hollow equivalent symmetry, and like a Z2 cross Z2 symmetry with mixed anomaly is a hollow equivalent to Z4 symmetry in 1+1D, and this 3Z2 with some kind of triple mixed anomaly is a hollow equivalent to this D4, this non-abelian symmetry, and there's another triple mixed anomaly, and this 3Z2 would equivalent to this Q8 non-abelian symmetry. And in general, in 1+1 dimension, the G symmetry is a hollow equivalent to the rep G symmetry. Okay, and when the G is non-abelian, the rep G symmetry actually is an example of a non-invertible symmetry. So let's just describe this non-invertible symmetry in some more details. So let's consider a n-dimensional lattice where the state live on the link. So it's a similar to the model to the second model we start here, except now on each link we have a degree freedom labeled by the group. Yes.
So in your example, A site and A link had the same categorical symmetry, and then their respective A trans were hollow equivalent?
Yes, yeah, that's right.
Is that always true if two symmetries have the same categorical symmetry that their A trans will be hollow?
Yes, that's definition. You know, for the symmetry belong to the same hollow equivalent class, their transformation algebra by definition are hollow equivalent. But however, this transformation algebra may not be related by unitary transformation, but they related by duality transformation. So actually, that's exactly what Shu-Heng talked about. You know, there's a usually some maybe non-invertible duality transformation led to the transformation. I think that in Xie Chen's next week, she probably will talk about the sequential operator, sequential quantum circuit, which can generate this kind of duality transformation, which map one. Sorry. Okay. Yeah, which map one algebra to another transformation algebra. Now, these two algebra may be connected by some kind of sequential quantum circuit. Yeah, something like that. Yes.
Hollow equivalent systems will have the same low energy dynamics. That is if you restrict to the symmetric excitation.
Yeah, I don't know. So that it's a yeah. Well, these two models have the same low energy dynamics. Maybe let me make a more precise statement. In both models, we have a transformation algebra, which defines so-called symmetric subhero space. The claim that within the symmetric subhero space, two models are identical. They have same energy spectrum, same everything. But however, there's a sector charged subspace. Because symmetry are different, the charged subspace is totally different. But the symmetric neutral subspace is identical. So that's another way to look at this duality transformation. In duality transformation, the symmetric subspace of one model map to the symmetric subspace of another model. Although the two models have different symmetry, they define symmetric subspace differently, but the symmetric subspace can map into each other identically.
Charge subspace always gapped, or are there cases where the charge subspace is gapless?
May not be gapped. Yeah. Yeah, this is a very interesting question. If a charge subspace, well, the charge subspace is gapped, like probably I would say the gap, because the charge sector do not contribute to heat capacity. They contribute some global quantum degree freedom. But if you restrict your symmetric symmetric subspace, you will saturate the heat capacity and in a submodel limit. Yeah. So probably that means the charge excitation should be gapped. Yeah. Okay. So here I try to, because it's a rep-G symmetry, is a very simple non-invertible symmetry, so just have some description for that. So the model is that we have a degree freedom live on the link, but the degree freedom labeled by the group. Okay. So the transformation algebra basically is a Wilson line. You know, you have degree freedom in a link labeled a group. It's like a gate theory. Then you can define a Wilson line operator, which basically you pick a representation of a group, then using this representation to get the matrix, and the product matrix, and take a trace to get the Wilson line operator for some loops. And this operator is diagonal if you basis is labeled by the group element. It's just diagonal. So Wilson operator just give you a phase factor. Okay. And this Wilson operator can be used as a transformation operator. And but this transformation operator have an interesting property that when you multiply two Wilson together, you don't get a third Wilson line. But for non-abelian group, you may get some kind of NIJK or NQ1, Q2, Q3, which is coming from decomposition of representation. This Q representation have this kind of tensor product decomposition. And this coefficient NQ1, Q2, Q3 would appear in the algebra of this Wilson loop operator. So that's it. So that is just an example of this non-invertible symmetry. But actually, in n-dimensional space, this non-invertible symmetry, because defined by line operator, is actually it's n-1 symmetry. And again, because from the gauging, so people who are familiar with gauging, you know, this kind of model actually is a gauging of an ordinary model where degree freedom linear on the side, and you have a G symmetry. And so actually, this non-invertible symmetry is a hollow equivalent to a G0 form symmetry. So in some sense, this non-invertible symmetry is not that exotic because it's equivalent to ordinary zero form symmetry. And in Shouheng's talk, he talked about some kind of more so-called intrinsic non-invertible symmetry, which is not due to any group-like symmetry. So that's a more non-trivial. So those intrinsic non-invertible symmetry usually come from some kind of duality map in the self-dual models. And so here in later in this talk, I will maybe give some other way to construct this non-invertible symmetry, but from this local operator subalgebra. There's other way to construct this non-invertible symmetry. Okay, so that's kind of an introduction, you know, how we define symmetry, you know, what's a equivalent class and etc. And so now we are facing a question that is, you know, once we define symmetry in this microscopic sense, what is the mathematical framework to describe those symmetry? Usually we say, oh, maybe group theory. Well, now we know group theory is not enough. Then you may say, oh, maybe higher group theory. And it turns out higher group also not enough. And it turns out that we have these two claims that the hollow equivalent class of symmetry in d-dimensional space are classified by a Braided diffusion n category in the trivial width class. And the trivial width class means this Braided diffusion n category actually is the center of a fusion n category. And the second claim is that that's for hollow equivalent symmetry. The second claim is just for symmetry. Normally free symmetry in n-dimensional space are classified by so-called local fusion n category. If you drop anomaly free condition, then you have a very natural result. The general symmetry are classified by the fusion n category. That's it. Okay, so these two claims using some fancy mathematical notion like a category, local category, things like that. So what are those category? Oh, another thing I just try to say that once you know this fusion category, we can see that the two symmetry described by these two fusion category are hollow equivalent if their center is the same. So we can also know when two symmetry are hollow equivalent. And so what is a fusion higher category, actually? So actually, the fusion higher category is nothing, just a theory, mathematical theory to describe excitations. But now the excitation can be extended, can be string, can be membrane, can be particle. And then when you have those kind of situation, naturally, fusion higher category is a theory to describe excitations. So here I gave an example in 2 plus 1D space-time. And then in this slide, we have a worksheet describing the string excitation. Okay. And then the domain wall or interface between 2 string excitation is a word line. That's a point-like excitation. Okay, that's a point-like excitation. And then on this word line, you may have a point. Again, you have an interface of word line, which is instanton. It's an operator, which is changing one particle to another particle. Okay, so now we have 3 layers. So the first layer is called the object. The interface of the object is called one morphism. And the interface of one morphism called a 2 morphism. And that's it. So this is a fusion 2 category. So that's it. It's no more than that. Yeah. Actually, there's more than that. But roughly, it's just that. There's many other conditions, but roughly, it's pretty natural. It's a pretty natural theory to describe excitation. So nowadays, when I heard a category, I thought it's just theory to describe excitations. That's it. Okay. And then, so now how does the fusion category relate to the symmetry? In the symmetry, we have a symmetry charge. Especially in the higher form symmetry, the symmetry charge may be 1-dimensional, 2-dimensional. Okay. And so therefore, this symmetry charge of a symmetry would form a fusion N category. Yeah. And so therefore, we have a fusion N category describing symmetry charge. And then in Shouhen's talk, we heard that the symmetry can also be described by symmetry defect. This topological defect, which corresponds to symmetry. The topological defect, the symmetry defect can also fuse and things like that. And they also described by a fusion N category. So we have a fusion N category of symmetry charge and the fusion N category of a symmetry defect. Okay. Okay. Now come to the second claim is that there's we can use the fusion N category of a symmetry charge to classify anomaly-free symmetry. Equally, we can also use a fusion N category of symmetry defect to classify the anomaly-free symmetry. Actually, for anomaly-free symmetry, they have a symmetry charge, and both symmetry charge and the symmetry defect are there. They are described by fusion N category. And so actually, the symmetry charge and the symmetry defect, these 2 fusion N category have a duality relation between them. So I will come back to this in a moment. However, for anomalous symmetry, the things a little bit change. For anomalous symmetry, we have a difficulty to define category of a symmetry charge. Why? Because anomalous symmetry is characterized by some symmetry which is lack of a symmetric gapped ground states, symmetric trivial gapped ground states. If you think about what is symmetry charge, actually symmetry charge is defined as an excitation above these trivial symmetric ground states. If you don't have a trivial symmetric ground states, then we have trouble to even define what is symmetry charge. But for some reason, the symmetry defect always well defined, always there. Okay, so therefore, we always have a fusion N category of a symmetry defect. In that case, we don't have to use this local condition. So any fusion N category would describe a symmetry. So and this way, this fusion N category of a symmetry defect would classify the anomalous non-invertible symmetry. Okay, so that is a picture. Then there's this qualifier local. What do you mean by local fusion N category? This localness actually is yeah, maybe let's describe local first. This localness is really from this picture. That is we have local, we have a fusion n category. Then this a fusion n category. Yeah, maybe I should not skip the first one. This usually you have a fusion n category. This fusion n category usually is have a so-called gravitational anomaly. Okay. What I try to say is that we don't have some kind of lattice model in the same dimension whose excitation are precisely described as a fusion n category. Usually we don't have that. But usually what happens is that this fusion n category describing excitation of a boundary of some topology order. So in that sense, we say they have an anomaly. But this boundary of topology order actually is characterized by the braided fusion category. Okay. So the braided fusion category, again, we have same graph, but here we increase spatial dimension by 1, so 3 plus 1 dimension. In this case, the string in the 3 plus 1 dimension, they can braid around each other. So there's a braiding there. Okay, but otherwise will be similar. So the braided fusion category and the fusion category is similar. Just we have one higher dimension, so the excitation have room to go around each other to braid. And then we have to record this some data to describe this braiding operation. Okay. And so usually for the topology order in n dimension, topology order in n plus 1 dimension, their codimension 2 excitation and codimension 3 excitation, and etc. They are described by this braided fusion n category. So this braided fusion n category again just describe this topology excitation in topology order. That's it. But we start with a codimension 2 excitation, and then so we have this braiding. And then this so then we have this so-called topological holographic principle. That is the boundary of a topology order would also have a boundary excitation. The boundary excitation would describe by the fusion n category. Okay. And this fusion n category describing boundary excitation and the braided fusion category describing excitation in the bulk have very close relation. This topological holographic principle says that the boundary fusion n category determine the bulk braided fusion n category. So the boundary determine bulk. So that means if you know the boundary, then we know the bulk. So there's a functor called the center functor, which map the boundary fusion n category to the bulk braided fusion category. So this Z is generalization with dream field center for one category. So, but in higher dimension, we also can define this so-called center functor. But in physics, this center just taking the bulk. That's it. So in physics, we say this R, if you view R as a quantum field theory, we say, oh, this quantum field theory have a gravitational anomaly. The gravitational anomaly described by topology order in one higher dimension, according to this anomaly inflow picture. And this functor just describing this anomaly inflow picture. So that's kind of modern way to describing this anomaly inflow. Okay. And so using this boundary bulk relation, now we can define this a local fusion n category. So this local fusion n category basically is that the statement is the following, and the fusion n category is local if there exists another fusion category called the R tilde, so that they have a same center. So that means that both R and R tilde can be viewed as the boundary of a topology order in one higher dimension. The local condition is such that when you have stacking this two boundary, R and R tilde boundary, via this common bulk, then what you get, this slab became a trivial topology order. Okay, and so the fusion category, local fusion have these properties. Okay, and this property really define this anomaly-free symmetry. So actually, this construction, because this is like a symmetry charge, symmetry defect, this is like a symmetry charge. And their stacking became a trivial phase. Actually, this is a trivial phase, trivial topology is actually it's a symmetric trivial states we just use to define this anomaly-free symmetry. Intuitively, why this definition looks kind of strange, but intuitively really is following. We have a fusion N category. There's a possibility the excitation in this fusion N category coming from some non-trivial topology order in that dimension. And when you have that non-trivial topology order, some topological excitation like anions, just from non-trivial topology order in that dimension, then this actual topology cannot be cancelled by any other boundary. So if this fusion N category have a more anion than necessary to describe a symmetry, then those actual anions cannot be cancelled by any other dual fusion category. And so that fusion category is not a symmetry charge. It's not describing symmetry. And so this condition really say that it's a fusion category. Just all their excitation can be viewed as symmetry charge. They all come from bulk. They all come from this bulk, and so therefore they can be cancelled because there's no actual. So this is the one way to say abstractly what kind of symmetry charge are really symmetry charge. They are not topological excitation. Yeah, that's an intuition. Okay, so this fusion. So the local fusion N category always have a dual. That's the definition. And so actually this pair is one is a charge, one is a defect. And but which one is a charge, which one defect is your choice. Okay, so that is a hollow equivalence. If you pick one as a charge, another defect, or vice versa, you just get a hollow equivalence symmetry. Okay. So yeah, with this introduction, so let's look at this. Now I want to try to explain the first claim. Why we claim that the hollow equivalent class of symmetry classified by the Braided fusion category. How that picture, where that picture come from. We try to get some kind of a general picture for that, some explanation for this picture. Okay. So here we just take a little detour. That you want to define the homomorphism between quantum field theory. We know that's a homomorphism, very important mathematical concept, like a homomorphism between two groups means that these two groups have some similarities. And because it's so important, we want to define the homomorphism of quantum field theory, because quantum field theory is very important. And typically, the morphism between two things are defined by their domain wall. So very naturally, we have a quantum field theory, another quantum field theory. If there's a domain wall interface, maybe the interface, then we say, oh, there's a morphism between two quantum field theory. We can do the similar thing for anomalous quantum field theory. Anomalous quantum field theory means that they themselves have no UV completion. And they are boundary of TQFT of topology order in one higher dimension. Okay. So therefore, naturally, follow the same logic. The morphism between two anomalous quantum field theory basically is an interface between these two quantum field theory plus interface of the bulk topology order that's describing anomaly. Okay, so this is a very natural thing to do. Okay, but however, this definition for some reason is not very useful for our purpose. So maybe useful for some other purpose, but not useful for our purpose. But we want to follow the similar idea to define a refined notion of a morphism, something more refined. Yeah, this more refined is really this picture. And but to explain this picture, we have some physical motivation. Physical motivation is called the low energy equivalence. So we try to say that because here we are interested in the gapless quantum field theory or something with low energy excitation. Then we say that if two quantum field theory are identical, if you're stuck with some kind of gapped TQFT or some gapped system with a very large gap, then the low energy, these two quantum field theory should be equivalent. Maybe only some global sector are different, but the local property, they're all the same. Yeah. So therefore, so this gets some notion of a local low energy equivalence if these two quantum field theory became identical after stacking with some gapped TQFT. Okay. Then we try to do this for anomalous quantum field theory. So this is an anomaly-free one. For anomalous one, we can try to do similar thing. Then we say we have an anomalous quantum field theory, have another anomalous quantum field theory, and whether they have a similar local low energy excitation or not. And in this case, what we can do is that, these two anomalous quantum fields may even have different anomalies. So the bulk may be different because bulk is gapped. So it doesn't matter. Attaching a gapped bulk do not modify local low energy property. And also between these two bulk, we may have a gapped boundary. And that also do not change local low energy property. So this became this general feature of this homomorphism between anomalous quantum field theory. That is, this quantum field theory is equivalent. So now it's a more precise limit. This quantum field theory, in every respect, equivalent to this composite quantum field theory. This composite quantum field theory have a one boundary quantum field theory, have a bulk, have a gapped bulk, have another gapped boundary. Then, if this QFT prime is equivalent to this composition, like they have same partition function, same spectrum, things like that, then we say that there is a homomorphism between these two quantum fields. Actually, the map from the QFT to QFT prime, there is a local low energy homomorphism from QFT to QFT prime. And this local low energy homomorphism are labeled by this pair. And this pair, R tilde, this gap boundary, which already determine the bulk, because the bulk is the center of R tilde. And another, this epsilon, epsilon is this domain wall, which is transparent domain wall, is isomorphism. This epsilon means isomorphism. Okay. And this definition actually is pretty reasonable in the sense that if both QFT are gapped, then their excitation are described by fusion n category. Then this homomorphism became a homomorphism of fusion n category, which turned out to be this this functor between fusion n category. This definition is naturally produce the functor between fusion n category from mathematical sense. And we try to say that, well, this picture even works for a gapless system. So that defines the homomorphism of a quantum field theory. And this homomorphism actually is this local low energy equivalence have this picture. Basically, we say that the quantum field theory prime secretly have this layered structure, and just this wedge just amplify this layered structure. So basically, the boundary excitation on the QFT can shift to the QFT prime side, and remain to be low energy excitation in other side. But the other global thing may be different. But the low energy excitation all come from this QFT. I mean, low energy excitation in the QFT prime all come from QFT. It's just shift around. Yeah. So that is isomorphism. So in a sense, this means that the local low energy excitation can be embedded into local low energy excitation of QFT prime. And they saturate in a sense. If only think about this local low energy excitation, you already can produce heat capacity with some your finite error. Okay. So this is just a study of some kind of topology order and anomaly. How the gravitational anomaly and topology are related. So it's pretty abstract study of homomorphism. Seems to have nothing to do with the symmetry. But actually, a few years later, we realized that the gravitational anomaly is a symmetry. They are the same thing. They are really identical. In one sense, we can say that both the symmetry and the gravitational anomaly constrain low energy dynamics. So in that sense, they play similar role. Okay, but for generalized symmetry, they are really identical. They are the same thing. And one way to say they are the same thing is the following. We look at the symmetric subspace. We just restrict ourselves to the symmetric subspace. For any symmetrism, we can do that. We restrict ourselves to symmetric subspace. Then we notice that this allowed perturbation are local symmetric operator. Again, this act within the symmetric subspace. So symmetric subspace almost like a universe. If you only allow symmetric perturbation, we never get out of it. So it's a self-contained universe. But when we view everything from a symmetric subspace, we have trouble. The symmetry transformation acts trivially. We don't see any symmetry transformation. So there's a serious issue, how to identify symmetry, how to identify group if you restrict yourself within a symmetric subspace. So it's kind of strange. We don't know symmetry unless we break it. but here you want to know symmetry without breaking it. Can we do that? So this is really the kind of philosophy in this consideration. Okay, but the one idea is that when you restrict yourself to the symmetric subhilbert space, this symmetric subhilbert space no longer have a tensor product decomposition. Original total Hilbert space have a tensor product decomposition, but the symmetric one don't. And then there is some study that the boundary of topology order also don't have a tensor product decomposition. So in some sense, the gravitational anomaly actually is a feature that the Hilbert space don't have a tensor product decomposition. Is a sign for gravitational anomaly. So from this lack of tensor product decomposition, we make a connection to the gravitational anomaly. So again, this is a very this is not a very strong argument, but at least you see there's at least some linkage between the two. The symmetry and the gravitational anomaly actually is the same thing.
Question?
Yeah.
What is a non-invertible gravitational anomaly?
Usually, so here the definition of gravitational anomaly is different from our traditional one. The traditional definition is a diffeomorphism, non-invariance path integral. Here the definition is a lack of a lattice UV completion. The obstruction of a lattice UV completion is defined as a gravitational anomaly. And then the
Standard model of particle physics suffered according to this definition from non-invertible gravitational anomaly. Is that right?
no, actually I believe there's a lattice realization standard model. Yeah, even though they have chiral fermion, there is a lattice realization, at least as iso10 for that. And even for SU, I think standard, yeah, I think they have a lattice realization, yeah. But however, there's some suppose you have this, you have some kind of suppose you have a theory, which you only have a charge Z2 charge. You only have Z2 charge, but no Z2 flux. Then if you have a theory with only Z2 charge as all non-trivial topological excitation, then that theory have a gravitational anomaly. In a sense, if you do the lattice model to realize Z2 charge, you also have some kind of additional thing, yeah. So so basically, you say that although this symmetric subspace is not realizable as a lattice model, but it's realizable as a boundary. So maybe maybe I can make this. So actually, the claim one actually became this picture. Not the more precise statement. We say that this symmetry is classified by this Braided fusion category. What that really means? It really means the following. When you have a symmetry, then you can restrict yourself to the symmetric subspace. Then the dynamics within the symmetric subspace is completely and fully and exactly simulated by the boundary of a topology order. And this topology order are described by this Braided fusion category. Okay. So therefore, instead of studying symmetry, symmetry transformation, and those things, we just study a boundary of a particular topology order. And the topology can only simulate the symmetric subspace. And there's no extension on the boundary which is charged. It's kind of like when you have, if the bulk is a gauge theory, then the boundary is always in the charge neutral sector, the gauge invariant sector. So, but this picture can generalize. So this became a precise statement that is we can use in the SymTO or SymTFT to describe, to exactly simulate, using their boundary to exactly simulate the symmetric symmetric system. And this picture is coming from this homomorphism just described. You can see in the homomorphism in the quantum field theory. So let's consider special case where we consider anomaly-free quantum field theory, whose bulk is trivial. Then we say it's kind of equivalent to some hollow equivalent to some anomalous quantum field theory with non-trivial bulk and with some boundary. So if you look at this picture, we try to discover hidden gravitational anomaly inside anomaly-free quantum field theory. We say, oh, we start with anomaly-free quantum field theory, but there's a hidden anomaly. We can view this anomaly-free quantum field theory as anomalous quantum field theory. They have same local extension. So we try to discover gravitational anomaly inside anomaly-free theory. But when you say gravitational anomaly is a symmetry, then try to discover gravitational anomaly became try to discover symmetry. And this is what we want. You know, when you have anomaly-free quantum field theory, although it have a symmetry, but you don't know it, then you try to find a decomposition. If you find this decomposition, then you say this anomaly-free quantum field theory have an anomaly and also have a symmetry, actually. So this really so finding this decomposition is a way to finding symmetry. And so this really led to this picture. For example, if this quantum field theory have a G symmetry, some group G, then the bulk would be the G gauge theory. And so this can be this anomalous quantum field theory, or maybe within the symmetric subhilbert space, is a boundary of this topology order. So this is this way, this kind of holographic way to look at the symmetry. And I think that's the key message. So for every symmetry can be looked at this way. And the interestingly is that this picture also kind of coincide with the two definitions we have. There's a hollow equivalent class of a symmetry and a symmetry. It turns out that this bulk topology order, this M, really is one-to-one correspond to this hollow equivalent class of the symmetry. However, if you supply this additional gapped boundary on the top, then this pair, the gap boundary plus bulk topology order, this pair describe a symmetry. Yeah. And but actually, because the boundary different bulk, so actually this boundary alone, this fusion category on the boundary alone already determine the symmetry. So that's led to the result that the fusion category classify symmetry, but the braided fusion category classify hollow equivalent class of a symmetry. So that is so that really led to this picture. To study symmetry, we just study the boundary for topology order. And actually, this there's two terms. It's either SymTFT or SymTO. They are really the basically same meaning, but with a little different emphasis, which probably is important. You know, for the SymTO, this term emphasizes there is a lattice UV completion in the bulk. There's a lattice model. And this lattice model don't have any symmetry. They emphasize the bulk have no symmetry, just have topology order, no symmetry. Lattice model have no symmetry. They break all the symmetry. In a SymTFT, there is an issue that sometimes SymTFT may have an automorphism, have a symmetry. Then there's an issue whether bulk have a symmetry or don't have a symmetry. The SymTO just emphasize the bulk, even there's an automorphism, the bulk have no symmetry. Yeah, and this may become important because if a boundary have some this additional symmetry correspond to the automorphism sim TFT, then this additional symmetry on the boundary actually is really not there because the bulk lattice regulation break all the symmetry. So this additional automorphic symmetry is not really there. So there's a slight different emphasis here, but otherwise these two concepts is almost the same. Okay, so maybe in last 5 minutes I try to so what I described so far just the pictures and looks like just some wishful thinking. And so now I do some more serious calculation. Can you do some more serious calculation to support this picture? So what do you want to achieve? You remember we define symmetry using this local operator subalgebra. That's a microscopic definition. Then at the end we make a claim. The symmetry are described by Braided diffusion n category. So that suggests that we should be able to derive the Braided diffusion n category from this local operator subalgebra. So how to do that? Okay, one way to do that is to use this so-called a patch operator, or more precisely the transparent patch operator. Okay. So the motivation is the following. This local operator we have, the local symmetry operator or local operator we have, correspond to charge pair equation operator, like a create a charge, anti-charge in the neighboring site, because they have totally neutral. They're like a charge pair operator, or maybe like a hopping operator for charge pair of charge. Similarly, this local operator can also be viewed as the hopping operator of a symmetry defect. It creates a symmetry defect and anti-defect. So like a hopping operator or like a currents. Okay. And the most important thing to recover the diffusion n category is to recover the charge itself. What is a charge? So if you know the hopping operator of a charge, how do you recover charge itself? The one way to do that to link many hopping operators together. Then you get a string operator. Then at the two ends of string operator, you have a charge, anti-charge, but very far apart. Then that's a way to discover there's a super selection sector hidden there. When you discover this huge super selection sector hidden in your local operator algebra, you actually discover the symmetry. Okay, so this is really the idea. So formally speaking, that we want to multiply this local operator together to construct extended operator, such that the bulk of extended operator is a commute with all other local symmetry operators. So bulk is invisible. The boundary is visible, but the bulk is totally invisible. And when you have any operator with an invisible bulk, the boundary would describe a super selection sector. So that's basically the idea. So therefore, we want to use a multiplication of a local operator to construct a patch operator, which the bulk is invisible transparent. This invisible bulk actually is a topological defect. This is the meaning of topological in topological defect. Means it doesn't matter where the defect is the same thing. That means transparency of the bulk. In general, this patch operator should be MPO operator. May not be just a simple product of many local operator. Maybe some MPO operator. Actually, I don't know. So I know the simple case. In the most general case, what is the efficient way to describe most general case? Maybe still a little bit open. It could be sequential operator. Yeah, maybe sequential operator may be simpler than MPO operator. Maybe using sequential operator, sequential quantum circuit describing this. Maybe that's another very good ansatz to do so. Okay. Yes.
This patch operator only acts on the physical Hilbert space?
Yes.
Yeah,
the dangling bound really means in fact when you have this MPO, there may be actual index from the bound dimension, but they're just an index of operator. They are not really degree freedom. Yeah. So the MPO really says that this operator may have a labeled by some actual index, and those which become effective boundary degree freedom. Okay. For example, for 1 plus 1D Z2 symmetry, this symmetric local operator algebra, subalgebra is given by the ZZ and X. And then we can multiply many neighboring Z together and to get 2Z operator which are far apart. So this Z operator actually is a Z2 charge equation operator, which is far apart. So then we kind of discover one end is a single charge operator. So that's Z2 charge. Okay. And when you multiply many X operators together, you also get this transparent patch operator, where this is like a transformation, symmetry transformation on the patch. In the bulk patch, we don't do anything, but on the boundary, we create a symmetry defect. So the boundary of this this operator is a symmetry create a pair of symmetry defect. And from this symmetric patch operator, yeah, then we can calculate the categorical data. For example, by multiply 2 operators together, you make another operator which is associated the fusion rule. And then because this patch operator is like a hopping operator of a defect, by putting this hopping operator together in a certain way, you can compute the statistics of a boundary defect. Okay, and also you can also compute the F symbol, which is given by in this paper. Basically, again, this a hopping operator in different order, arranged in different same set hopping operator, but arranged in different order. Then there may be different by a phase factor, which is F symbol. And again, we know this for simple examples, and for most general case, I think it works, but one need to maybe there's some subtlety. One really need to work this through. But the general idea is that this patch operator is like a string operator whose boundary is onions. Then from the algebra of the string operator, you can recover the onion quantum dimension, onion statistics, their mutual statistics, and F symbol, and all these categorical data. But certainly, when you have memory operator, the boundary will be string. Well, that's maybe open question. That's how to discover data for higher category. Presumably, using similar idea, you should discover data for higher category. Yeah. So this is really a kind of some kind of suggestion we can use in the local operator algebra, and via this transparent patch operator and via the algebra of transparent patch operator, you can compute the Braided diffusion category, and which compute the symmetry. And so maybe let me just make some remark. Is that so for example, this is a picture to describe Z2 symmetry. Just for Z2 symmetry in 1 plus dimension, the sim TO just a Z2 gauge theory. Okay, have a excitation this 1, E, M, and F, this Torah model. Okay, then so this Z2 gauge theory is describing this hollow equivalent class of Z2 symmetry. Then in this hollow equivalent class, we have 2 Z2 symmetry. One is a charge E condensation. This E condensation, another is M condensation, give you 2 different boundary. So in principle, you may have 2 different Z2 symmetry belong to the same hollow equivalent class. But the funny thing is that these 2 symmetry happen to be the same, because this VEC Z2, REP Z2 is the same fusion category. So these 2 different condensation actually led to the same Z2 symmetry. So we only have 1 Z2 symmetry in this class. Okay. And then the top boundary describe a symmetry. Lower boundary is dynamical boundary, so we have a 180-degree freedom in the lower boundary. And actually, the string operator, which create a pair of M onion, a string operator in the box create a pair of E onion, really behave like a symmetry transformation operator. So therefore, the symmetry transformation, Z2 symmetry transformation, can be viewed as a string operator in a bulk. And this picture is very useful. That's one thing I want to emphasize here. That if the boundary of a string operator is onion, is a boson, then this corresponding symmetry is anomaly free. If end of string operator is onion, have non-trivial statistics, then it is the symmetry will be anomalous. However, when you have two symmetry, means you have two string operator, whose boundary anion have a non-trivial mutual statistics. You have mixed anomaly for these two symmetry. However, if a boundary anion is a non-abelian anion, then you have a non-invertible symmetry. Yeah, to me, I feel this is a better way to look at the non-invertible symmetry. Basically, is that in this holographic picture, the symmetry transformation is always given by the string operator in the bulk. However, if the boundary of string operator is a non-abelian, then that symmetry is a non-invertible. Yeah. So so basically, this is a kind of a bird eye view of the generalized symmetry, but from one higher dimension. And we have some classification of a modular tensor category in 2+1 dimension, which really classify the symmetry in 1+1 dimension. So we can have some general picture. We can see that when you have a rank 4, that means the bulk have 4 anions. That means the total number of symmetry charge and symmetry defect is 4. Then we actually have a 3 hollow equivalent class of symmetry. Okay. And from group point of view, we know 2 of them. One is anomaly free Z2 symmetry. There's an anomalous Z2 symmetry. That's 2. So the third one is a new one. Yeah, there's a third one, which is not an anomaly free Z2, also not anomalous Z2 symmetry in 1D. The third one actually given by the double Fibonacci model. Okay. Yeah. Yeah, the bulk is a double Fibonacci. Then the string operator create a Fibonacci anion is really realizing this non-invertible symmetry, because the end of this anion is a non-abelian Fibonacci anion, so this is non-invertible symmetry. Okay, yeah, I will stop here. Yeah.
A little bit late, so but you have a question, yeah. Well, you have a few more slides.
Okay, maybe just I just say it. Yeah, let's say just yeah. Maybe this is why in fact is my last slide. So this holograph picture also have a way to understand the SPD states of a non-invertible symmetry. So remember, for anomaly-free symmetry, we have a pair of fusion category for charge and another one for the defect. When you stack them together, you get a trivial phase. So this trivial phase actually is symmetric product states for this particular non-invertible symmetry. That's a trivial SPT. What is non-trivial SPT? We can have this slab construction. We just insert automorphism in the bulk. The bulk SymTO may have automorphism. Another is that in the bulk, we may have a transparent domain one or invertible domain one in the bulk. When you insert this invertible domain one in the bulk, then things change. Then this combination with the invertible domain one became SPD states. So this is basically, they say that the automorphism in the SymTO classify SPT for that SymTO. There's a little bit of catch is that because the top boundary is a symmetry defect boundary, so this automorphism may change the condensation which produces this top boundary. So there's condensed algebra which produces the top symmetry defect boundary. And we need to require that this automorphism leave this condensed algebra unchanged, so that we are talking about same symmetry. So the SPD of a fixed symmetry. So require this automorphism leave this condensed algebra unchanged is like to say we fix symmetry. So that's it. So automorphism, which is fixed condensable algebra, which produces the symmetry defect category, that automorphism of a bulk SymTO classified as SPD state. So this is one way to look at SPD states. And the funny thing that in this point of view, we seem to be able to define SPD state even for anomalous theory, anomalous symmetry, because we don't need this bottom boundary, anything. We just have some SymTO, some top boundary, then we have an automorphism which leave this condensed algebra unchanged. And this, maybe we can formally define this invertible domain wall in the bulk is like adding a SPT order. But however, in this for anomalous symmetry, we don't have a symmetric product states, which is as a trivial SPT. So the meaning of SPT may be slightly different. We have a notion that we have two states that differ by SPT, and but I think that notion probably can be defined. Yeah, I think that these are my last slides. Yeah, so this holograph picture have a, is I feel very useful way to look at a lot of things we know before. Yeah.
There's no 26.
Oh yeah, this is just a it's just a joke.
I feel like
sorry. I was a prisoner, and this is a symmetry.
now we see more. Let's release the prisoner.
I'm used to it. Yeah, yeah, that's my older view of symmetry.
It's time to go to the coffee break, so let's thank Xiao-Gang for it.